Hey everyone, this is Gary. I'm off this week visiting the beautiful Commonwealth of Puerto Rico, where hopefully I will not be stranded due to a hurricane. I've hand-selected some of my favorite episodes for you to enjoy this week, which, statistically speaking, I know most of you haven't listened to yet. I will be back again next week fully rested with fresh new episodes for you to enjoy.
The biggest thing that there is, and the biggest thing that there can be, is infinity, right? It literally has no bounds. In fact, thinking about infinity can quickly give you a nosebleed or a headache because our finite minds can't really grasp just how enormous it really is. However, what if I was to tell you that there's something even bigger than infinity? Or to be more accurate, there are infinities that are bigger than other infinities. Follow me down the rabbit hole as I investigate infinity on this episode of Everything Everywhere Daily.
This episode is sponsored by ButcherBox. One of my favorite things to make at home is surf and turf. That, of course, is some form of steak paired with some form of seafood. My go-to surf and turf meal will usually be a ribeye steak fried in an 80-year-old cast iron pan that was passed down from my father, coupled with some form of shrimp fried in butter. If you like surf or turf, ButcherBox is your hookup. They only carry 100% grass-fed, grass-finished beef, as well as wild-caught and sustainably harvested seafood. There are no additives or preservatives, and it's shipped freshly frozen to your door. When my ButcherBox shipment arrives, I feel like it's Christmas morning. If you like surf and turf, you are going to love their current special. Sign up today at butcherbox.com/daily and use code DAILY to get 2 100% grass-fed filet mignons and 2 wild-caught lobster tails for free in your first box, plus $20 off your first order. Save $60 on 2 of their highest quality cuts and save the legwork with their doorstep delivery. This exclusive offer only lasts until September 6th. Go to butcherbox.com/daily and use code DAILY to claim this deal today. This episode is sponsored by newspapers.com. If you listen to this podcast, then you're probably a student of history. And if you love history, look no further than newspapers.com, your ultimate resource for exploring history. Newspapers.com is like a time machine. You can find out what happened on the day you were born or how significant moments in history were reported when they happened. You can see for yourself what newspapers at the time had to say about humans landing on the moon or the end of World War II. With over 800 million digitized pages from over 24,000 newspapers spanning 3 centuries, Newspapers.com provides an unparalleled gateway to the past, with newspapers from the United States, United Kingdom, Canada, Australia, and many other countries. For Everything Everywhere Daily listeners, Newspapers.com is extending a discount of 20% off a Publisher's Extra subscription. Just use the code EverythingEverywhere at checkout. Uncover the extraordinary with Newspapers.com today, and use the code EverythingEverywhere at checkout.
This is an episode I was very unsure about doing. I came up with the idea over a year ago when I first launched the podcast. The reason I was hesitant is that the ideas I'm going to talk about are much easier to explain if you can illustrate them. It's just hard to do in an audio format. But I realize this is a daily show, and if I fall totally flat on my face, I can just get back on the horse tomorrow with a brand new episode. The concepts I'm going to be talking about are actually not difficult to understand. They usually are only presented in a university-level mathematics course, but there are no equations involved. It's nothing more than ideas and concepts. If you don't get some of the ideas, feel free to go back and re-listen to a section or find some other sources online which can help illustrate the concept. My end goal is to prove to you that there are some infinities larger than other infinities. This will start in the 19th century with a German mathematician named Georg Cantor. Throughout history, mathematicians have had a difficult time dealing with the concept of infinity. Cantor took steps to try to rethink the very foundation of mathematics. To do this, he created what is called set theory. A set is an incredibly simple concept. A set is a collection of distinct things. A set can be made up of anything, tangible or intangible. The fingers on my right hand can make up a set. All the presidents of the United States can make up a set. Numbers can make up a set. Don't overthink the concept of a set. It really is as simple as what I just said. The things in the set don't even have to be the same sort of things. In fact, it's so simple you might be wondering what the big deal is. Well, as it turns out, this idea of a set is a very handy way to think about mathematics. For example, what does it mean if two things are equal to each other? Again, a very simple idea, but one which can be really tricky to answer when you get into the weeds. In set theory, two sets are equal to each other if there is a one-to-one correspondence to the members of each set. There is a one-to-one correspondence between the number of stooges and the number of wise men. Likewise, there is a one-to-one correspondence between the number of deadly sins, the number of Akira Kurosawa's samurai, and the number of Snow White's dwarfs. It also helps us define what a number is. 5 is equal to any set which has the same number of objects as I have fingers on my right hand. The number 5 represents the cardinality of a set with 5 members. So far, this is all really simple. So simple that you might wonder what the point is. It actually seems rather obvious. Well, a set can also have an infinite number of members, and this is where things get interesting. We can also use the same techniques to determine if things are equal on sets of infinite size. The infinite set that we'll look at first is the simplest such set, the set of natural numbers. This is just the set of the normal counting numbers that you're used to, 1, 2, 3, 4, 5, 6, etc. If you start playing with this set, then interesting things happen. For example, if you add any finite number to that set, the size of the set stays the same. To illustrate this point, let's assume that there's a hotel with an infinite number of rooms. You go to the front desk and ask for a room, but the front desk manager says that they're sold out. There are an infinite number of people filling up the infinite number of rooms, and they are sorry, but there's no rooms available for you. No problem, you say. Just have everyone move up one room. The person in room 1 goes to 2, the person in 2 goes to 3, etc. Now, room 1 is freed up, and there's a place for you to stay. You added a person, and still the infinite number of rooms have an infinite number of people. Nothing has changed. Now let's assume that an infinite number of people show up asking for a room. Again, all the rooms are sold out. This time, you can find space for an infinite number of people by having everyone move to the room which is twice the number of the room they were previously in. Room 1 moves to room 2, 2 goes to 4, 3 goes to 6, etc. Now everyone simply goes to the odd-numbered rooms, and you have space for an infinite number of people. Likewise, you can subtract a set of infinite size, and it won't change the original infinite set. For example, all of the odd numbers equally match up to the set of natural numbers 1 to 1, yet the odd numbers are half of the numbers. Any set which equals the set of natural numbers is called countably infinite. Now, before I said that a number reflects the size of a set. 5 represents the size of a set with 5 things. Well, what number represents this infinite set? You may have heard that infinity isn't a number, and that's true. Kentnor created a new number called Aleph Null, or Aleph Zero, to represent the number of this infinite set. Aleph is the first letter in the Hebrew alphabet, and he picked it because they were running out of good Greek letters to use in mathematics. This is called a transfinite number, and as you can tell from my above examples, it doesn't behave like a regular number. You can't just stick it into an equation like you would 3 or 7. Kenner then wondered if the set of natural numbers was the same as the set of all fractions, known as the rational numbers. There is an infinite number of fractions between any 2 points on a number line because you can always just divide by 2. Through a very clever technique, Kenner figured out that the set of all fractions was equal to the set of natural numbers. It was countably infinite. Imagine a graph with numbers going up the vertical axis and numbers across the horizontal axis. You can draw a line that connects every fraction. You snake your way connecting the dots starting at 1 over 1. Then you go to 2 over 1 and 1 over 2, where the numerator and the denominator add up to 3. Then you go to 1 over 3, 2 over 2, and 3 over 1, where the numerator and the denominator add up to 4. You can continue this indefinitely. All of the fractions are on a line, and hence are countably infinite. This was a surprising result, but the next result was even more surprising. The next question Kentnor had was if the set of natural numbers was equal to the set of real numbers. Real numbers are all of the numbers which can and can't be expressed as a fraction. A real number is expressed as an infinite string of digits. Pi is a real number, as is the square root of 2, and any infinite random string of digits to the right of the decimal point. The proof that Cantner came up with rocked the world of mathematics. It was probably even more clever than the technique he came up with for the rational numbers. And this is the part that might be hard to visualize, so listen closely. You can't really put infinitely long strings of numbers into any sort of order. So Cantner just assumed that you could make a list that was complete. It didn't matter what the order was, but you could make an infinitely long list that had every real number on it somewhere. Just so you're visualizing it correctly, it's an infinitely long list, and every entry on this list is an infinitely long string of numbers. With every possible number accounted for on the list, supposedly, Cantner then set out to create a new number. On this list, he took the first digit after the decimal point in the first number and added a 1 to it. If the number was a 1, it becomes a 2. If it's a 2, it becomes a 3. And if it's a 9, it becomes a 0. He then took the second digit in the second number and added a 1 to it. He then took the third digit in the third number and added a 1 to it. You can go diagonally down this list, changing the nth digit to the nth number. What you wind up with is a brand new number that cannot be on the list. Any number on that infinitely long list has to differ from this new number in at least one digit. The problem was, the stipulation was that the list was complete. It was supposed to have every number on it. And this is called a proof by contradiction. The implication of this contradiction was that the set of real numbers is bigger than the set of natural numbers. It is not countably infinite. This means that there is an infinity larger than infinity. The set of real numbers was given the transfinite number of Lf1. As I mentioned, this realization rocked the world of mathematics. Many people could not get their heads around it, even though it was true. This diagonal proof method was used by Kurt Gödel to prove his incompleteness theorem, which rocked the world of philosophy, when he proved that in any logical system, there are statements that cannot be proven. If you think the idea that there is an infinity larger than infinity is weird, it gets weirder. There are an infinite number of infinities, each larger than the next. One of the biggest outstanding problems in mathematics deals with these infinitely large sets. It's called the continuum hypothesis, and it states that there are no infinite sets between Lf0 and Lf1 in size. Mathematicians think this is true, but so far it has never been proven. So, yeah, there are infinities larger than some other infinities. The key to understanding this is the diagonal proof. It doesn't require any advanced mathematics, just understanding the idea. And there are many resources online to help you better understand the diagonal proof if you want to go into it some more. If you take the time to really understand it, and it's really not that hard, then you too will be able to prove to your friends at the pub that there is something actually larger than infinity.
The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Thor Thompson and Peter Bennett. I just want to thank everyone, including the show's producers, who support the show over on Patreon. If you'd like to support the show, just head over to patreon.com, which is currently the only place where you can get show merchandise. Also, if you want to talk to other listeners about the show, head over to our Facebook group or Discord server, both of which have links in the show notes.